Good afternoon, everyone. So, as Guido mentioned, the title of my work within the DIGIMAN project is the development of a novel smart surface for material flow handling. Today we are going to see the background introduction, the design, the simulation and the testing parts, and finally conclusion and next steps of the work. Just a few words on what are smart surfaces. These are a kind of non-prehensile transport system used to manipulate and handle material flows inside factories and warehouse. And the main characteristics are that they are programmable and modular. And these two characteristics make them more flexible and efficient compared to classic systems such as conveyor belts or vibratory feeders. There are a lot of technology that can be used to create these kind of surfaces. I focus mainly on the last one of this list, so the surfaces with the rotors. And I noticed that this kind of system usually take advantage of a lot of motors. So they exploit a lot of motors in each module, making them really complex to actuate, make really complex the actuation and the control. So I decided to work on the simplification of this fact, and I try to create a new surface without the use of motors. So this is the concept of the surface. It's modular, like the previous system that I mentioned, but exploits idle rotors. So they are not actively driving the object on top of the surface, but I can control only the orientation of their axis of rotation. So the rotor doesn't have a motor inside, so it's not spinning, but I can control only its orientation. And this orientation can be placed only in a discrete number of positions. So to compensate the missing actuation, since it's use idle rotors, I'm planning to use gravity, inclining the surface, or previous speed of the object. For example, in a transport line, you can imagine that there is a conveyor belt before the surface. Focusing on the single module, the idea is to use a spherical rotor, which is supported from below to be free to rotate in every direction, and is surrounded by pins that I use to define the axis of rotation. So the idea is, when I want to define the axis of rotation, is to select a pair of opposite pins and put them in contact with the sphere. And this contact defines the axis of rotation. When I want to remove this axis and select a new one, I detach these pins and I connect a new pair. And as you can imagine, when I have a rotor and its axis of rotation, there are two main forces between the rotor and an object that is moving on top of it in the contact plane. There is a force parallel to the friction axis, to the rotor axis, which is the highest one because the rotor cannot rotate in this direction. And there is a smaller one, which is perpendicular to the rotor axis, because it's due only to the resistance against rotation of the rotor. And I'm planning to use these two in order to manipulate the material flow. This is the design of which I came up to do this task. So here you can see some sections of the concept of the module. So you can see the idle sphere in the center, supported by smaller spheres, and the pins surrounding the sphere, and the actuation system is done with coils. So the idea is to select a pair of opposite coils, turn them on, they magnetize the pins inside, and this magnetization produces the attraction towards the central sphere and the contact for the axis definition. Now moving to the simulation part, I've done three main simulations. One about the material handling with MATLAB, a dynamic simulation with Adams, and a magnetostatic simulation with ANSYS. And the objectives in this case were to verify the functioning of the system, of the surface, verify the analytic model proposed, and performances, and also identify some parameters. Starting with the first one, the idea was, what I've done was implementing the analytic model proposed for the contact between the sphere and the object into MATLAB, and use this to evaluate some different tasks that can be done with the surface. So you can see, for example, in the picture, a sorting activity or a position tracking activity. And I use this environment to test also the performances of the surface. In the other picture, you can see the sorting rate achieved with the surface, changing the initial input of the object, so the initial velocity of the object, or the inclination of the surface. And this MATLAB simulation is useful because you can test in a very fast way different kind of situations, and it also allows the real-time control of the surface for the next step. Then moving to the dynamic simulation, the idea in this case was to verify if, with a dynamic model, if this concept of sphere and contact with the pins was actually working for creating these two handling forces. And I simulated a single module and the whole surface, which is the thing that I'm presenting here at Euspen with the poster, and see if this system is actually working for manipulating material, and also to evaluate the analytic model. So, for example, in the simulation of the surface, I've tested a sorting condition, and I measured with atoms the two friction forces that I mentioned before in the parallel and the perpendicular direction with atoms, and also with the analytic model. And I compared the two results, and it came up that the error between the two is almost zero for all the simulated time except few instants. But in this instance, the error was the absolute error was below 0.1 Newton, which in this case is very small. Another use of the dynamic simulation was to evaluate the MATLAB results. So I've done the same sorting simulations for with different inputs in MATLAB and in Adams, and I compared the two results to see the errors between the final position achieved with MATLAB and with Adams. For example, I've reported a graphical representation of this. You can see the magenta square and the black square are almost matching, and I've tested this for different inputs, and I've reported here some errors. The last simulation conducted was the magnetostatical one. The idea in this case was to estimate the magnetic force between the pin and the sphere, and I've used this in order to define better the shape of the pins, to increase this force, and to try different materials in order to select the best one. After all these simulations, finally I decided to build a prototype in order to practically see if the system was working, to improve the design, to understand what can be improved or not. And I use this also to measure some important parameters like the friction coefficients and to validate the analytic models. I've designed 3 test benches. The first one was to measure the friction coefficient the first measurement was to measure the friction coefficient when the axis of rotation of the sphere was in the same direction of the velocity of the object. And then I measured the opposite condition, so when the object direction was perpendicular to the axis of rotation. These 2 parameters were necessary for the analytic model. And at this point, with the analytic model ready for the validation, I built the second test bench to measure the 2 friction forces at the same time with the object moving inclined compared to the axis of rotation of the sphere. This way, I've been able to compare the real measurement with the analytic model. And the last test bench was used to measure the magnetic contact force that I was mentioning before. Here are some results, for example, some friction coefficients with different loads on the object, different materials in contact, so object and sphere. In the center, you can see the parallel force, the red one, and the perpendicular force, the blue one, obtained with the analytical model, the measurement with the second test bench, and the ADAM software. And changing the inclination between the object and the axis of the rotor. And then in the last picture, there are some forces, magnetic forces obtained with the last test bench, changing the shape of the pins and the materials in contact. And also the result with the software ANSYS. Yeah, to conclude, what I presented was the design of a surface in order to simplify this class of system, this class of smart surfaces with rotors. And now the idea is to, what I'm doing now is trying to build a small surface in order to include cameras and test in real time, measure in real time the displacement of the object on the surface and verify experimentally finally all the simulations done and all the tests done with one single model. Thank you for your attention.
We have time for one quick question. No quick question, but I have a question.
Okay.
Can you relate your friction results with the actual surface roughness in your model?
Surface roughness. What do you mean with surface roughness?
Really the topography. Or you assume the surface is smooth and then you simulate the friction.
I mean, with the test, I measured the friction coefficient between the sphere and the actual object.
Yeah.
So I think this is including the roughness, of the sphere, like an effect of more spheres together. Until now, I haven't done this, so I will see. Maybe there is another effect. Do you think there is another a different effect if I have more spheres together and the object placed on top?
I'm thinking
Was this
about
the question?
different objects at different roughness.
Ah, yes, of course, yeah.
And the spheres perhaps are more standardized.
Yeah.
And then you observe that change as a different friction.
Yeah.
But if the model already has the roughness, then it's mirroring what's in reality. It's maybe an idea for.
Yeah, I don't know if friction is only related to roughness, but
It's also.
yeah, of course. I've tested different materials, like cardboard, for example, because usually maybe can be used for transporting packages, and other materials. So, yeah, I want to consider more options, but I cannot test all the materials. But this idea is good if I can predict from before with the roughness what will be the friction coefficient, will be helpful.
Okay. Thank you.